Hello everyone. So today we are going to start our O-level chemistry class, and today our study content is the rate of reaction of the O-level syllabus, and from this book we are studying, this is chapter number 7, okay, the chemical reactions. We have already covered the redox reaction part and the reversible reaction part in the last previous question, in the last videos, okay. So today we are going to study the rate of reaction, and first of all, what we are going to start with the collision theory. Okay. Now, what is the collision theory? Okay. Now it's like that. If I tell you that two people, two person want to fight with each other. Okay. The Okay, so two people want to fight with each other. Now if they don't come into contact with each other, or if they don't hit each other, then they cannot fight. Okay, isn't it? So the thing is that for the two people to cause a fight between two people, the two people must come into contact. The two people must come into contact and then hit each other. Okay. So in case of chemical reactions, the same theme applies. Okay. Now for example, um, for example okay, now for example, if no, not this color. Okay, if hydrogen and chlorine, they react together to form HCl, okay, then the hydrogen molecules and the chlorine molecules, they must collide with each other, okay, to cause this reaction and produce HCl. All right. Okay. So the hydrogen and the chlorine, they must collide with each other, like, okay, this is a hydrogen molecule and this is a chlorine molecule, so they must, or there must be a collision occurring between them, okay, so that these two molecules react. Okay, now what do you mean by a reaction? A reaction means, what do you mean by a chemical reaction? A chemical reaction means when, just note this part, please write the question. What do you mean by a chemical reaction? Right? Okay. So, a chemical reaction basically means new, a chemical reaction basically means some older bonds are broken and new bonds are formed. Okay, so older bonds are broken and new bonds are formed. That is what we mean by the term chemical reaction. Okay, now the thing is that any kind, so to break the older bonds, so to break the older bonds, you need, you must collide the particles so that the collision between them breaks the bonds. Just like when, for example, two person, they are running towards each other. Okay, they are running towards each other like this. Okay. Sorry. Okay, they are running towards each other like this, and then there is a collision between them. There is a collision between them that causes their bones to get broken. Okay, so their bones are broken in the same manner, like if the two particles collide and if the bonds between them are broken, then there is a possibility that new bonds are formed between the atoms. Okay, so for a reaction to occur, first bonds has to be broken and bonds has to be formed. Okay, now here stop writing. Now listen. So new bonds, so older bonds are broken and new bonds are formed. Let me give you an example. Please write the example in your copy. For example, this is a hydrogen molecule, okay, and this is a chlorine molecule where two chlorine atoms are bonded together. And now, for example, this is hydrogen, okay, and this is chlorine, and they collide with each other. It's a very strong collision. Okay, so they collide with each other to break the bonds and separate the atoms. Okay, so the bonds and the bonds are broken. Look, here bond is present, but here the bond is absent. So the bonds are broken and the atoms are now separated. So what happens now is that the atoms now get joined together like this. Cl and H, Cl. Okay, so look here, what we have is that the hydrogen bond, the chlorine bond, they're broken, and HCl, that is the bond between hydrogen and chlorine, are formed. Okay, so this is what we mean by a chemical reaction, that older bonds are broken and newer bonds are formed. Okay, now do you think that suppose two persons running towards each other, and please listen carefully, two persons running towards each other, if they collide with each other, will all times their bones be broken? No, their bones will not be broken all the times, but if they collide with huge force, with huge velocity, then there's a possibility that their bones might be broken. Okay, so for a chemical reaction to occur, please note this down. For a chemical reaction to occur, the particles must collide with energy, with kinetic energy, so that the bonds between them are broken. Please write it down. I'm repeating it again. For a chemical reaction to occur, the particles must collide with enough kinetic energy so that due to collision their bonds are broken. Okay, so let me give you an example. For example, the hydrogen and chlorine. Okay, this is hydrogen, this is chlorine, this is hydrogen, this is chlorine. All right, so they collide with each other. Okay, so hydrogen have the energy 80 kilojoules and chlorine have the movement energy, for example, it's 80 kilojoules. Okay, so total energy they have 60 kilojoules, but when they collide with each other, in this case they remain as it is and they move away from each other, hydrogen and chlorine, isn't it? That means they collided, they have undergone collision, but the energy, the kinetic energy they had was not enough to break the bonds in hydrogen molecule or the chlorine molecule. Okay, now that imagine these particles now collide with energy 81 kilojoules. Okay, so hydrogen have 81 kilojoule, chlorine have 81 kilojoule. Now they collide with each other, and what happens is that you get individual hydrogen atoms and individual chlorine atoms. Okay, so when these particles collide, okay, this is just an example. Okay, take it as an example. So these particles collide with energy 81 kilojoules, and after undergoing collision with kinetic energy 81 kilojoules, their bonds are broken and we have got separated atoms, isn't it? That means the reaction has started since bonds are broken. So if the particles collide with a minimum energy of 81 kilojoule, they would react. That means if these particles have any amount of energy greater than any amount of energy which is equal to or greater than 81, then the particles would react. Okay, for example, if hydrogen and chlorine, they have 83, 84, 85, 87, 90, 100, etc., etc., they have this amount of energy, so their collisions are enough, their collisions are sufficient to break the bonds, because the minimum energy requirement is 81. Okay, so what is the minimum energy requirement? It is 81. So the minimum, this minimum amount of energy, this minimum amount of energy with which, please note this down, the minimum amount of energy with which the particles, if they collide, then the bonds would be broken and reaction would be started, is known as the activation energy. Okay, so the minimum amount of energy that that the particles must acquire so that they can react with each other is known as the activation energy. So if these particles have 81 kilojoule energy, then they would react. Okay, but this 81 kilojoule energy is the energy that the particles must have. Okay, here we are now going to differentiate between the activation energy and the energy what the particles have. Okay, so this 81 is the energy that the particles must have in minimum so that they can collide and react. Okay, now let me tell you something. And okay, so okay, so suppose I'm drawing a particle. Okay, this is a red colored particle. So this particle has got how much energy? Okay, so let this particle has got 60 kilojoule energy. Okay, now another particle like this, sorry, now another particle like this also have 60 kilojoule energy, but how much energy do they need so that their collision can cause a reaction, their collision can cause bond breaking? It is 81. Okay, so we need 81. So this particle has got 60 kilojoule energy, and how much more energy do we need to give him? We need to give this particle more 21 kilojoule of energy, isn't it? So more 21 kilojoule of energy, so that the particle gains in total 81 now, and for the same case goes for this particle also. Okay, so we also need to give 21 kilojoule of energy to this particle so that its energy, its kinetic energy or its movement energy now becomes 81. Okay, now they will, now in this case they will now react. Okay, so here they will not carry out any reaction, but over here they will carry out a reaction. Okay, so here the particles react, I'm writing R, and here the particles does not react. Okay, so after giving how much amount of energy the particles have started reacting, 21. Okay, and these 21 kilojoule of energy is what we are calling it as the activation energy. Okay, so activation energy is the amount of energy that must be given so that the particles would start reacting. Okay, this is not the activation energy, this is the energy that the particles must have so that they can react. Activation energy is the amount of energy that must be given. All right, okay, now let me make it straight. Suppose you, this is you. Okay, so you want to go to a shop and to buy ice cream. Okay, so you want to buy ice cream, and the cost of the ice cream is 50 bucks or 50 taka. Okay, but you have, so this is what the amount of taka that you must have to buy the ice cream. But right now you have say for example 30 taka you have. Okay, so how much more money do you need to buy the ice cream? So you need more 20, isn't it? So that 30 and 20 makes 50. Okay, so you must have 50, but right now you have 30, so you must be given more 20 taka to cause it 50. Okay, so this 20 here is what we are calling it as the activation energy. Okay, so guys, the activation energy, please write the definition. I'm telling, activation energy is the amount of energy that must be given to the particles so that they react. Okay, or they start reacting. So activation energy is the minimum amount of energy that must be given to a particle so that they start reacting. All right, okay, so that is the activation energy. Now, so now anything, so we have got to know that the collisions between the particles, they cause reaction. So any factor that affects the strength of the collision or the number of collision would also affect the rate of reaction. Okay, for example, let me get this straight. What we have over here, look at the factors. We have the surface area of the reactants, we have the concentration, we have the temperature, we have the light, and we have the use of catalyst. Okay, okay, now we will consult about this graph later on. Okay, so let's get to the factors. Okay, now all factors if employed or if applied more would cause the rate of reaction to go up. That means the rate of reaction would rise. For example, if you increase the surface area, the rate would go high. If you increase the concentration, the rate would go high. Okay. If you increase the pressure, the rate would go high. If you use catalyst, the rate would go high. Okay, so let's see why if you increase the surface area, the rate would go high. Okay, let's see. Okay, so for example, let me draw some clogged particles. Okay, some red particles which are confined in a space like this, and we have some green particles which are confined in a space like this. Okay, so here only between these surfaces there is a possibility of collision, like there will be a very few number of collisions. All right, like look over here, there will be very few number of collisions. Okay, but what would happen if okay, what about the surface area? Look here, sorry, here the surface area is this, here the surface area is this. Okay, so the amount of surface area or the amount of contact surface is very small. Okay, okay, now what happens if we sprayed all these particles? If we spread these particles, then what would happen? Let's see. Okay, so okay, we have spread the red particles and we have also spread the green particles. Okay, now look at the amount of contact they are now able to carry out, isn't it? So there is a large so they are able to collide or carry out collision over larger area, isn't it? Do you agree with me? You should. Okay, so the contact area between the particles is now larger. That means they can now come into contact more often. So the amount of contact and the amount of collision between the particles would increase, and therefore the rate of reaction would also increase. Okay, so please note it down that if surface area of the reactants increase, then the amount of contact surface between the particles also increase, and so there are more collisions, and so the rate of reaction would go high. Okay, okay, so the surface area, look what did they say. Okay, so here they said many things about surface area, like look what did they say. They are carrying out a reaction between HCl and calcium carbonate. Okay, so in the reaction between HCl and calcium carbonate, the observation is the production of carbon dioxide. The more faster carbon dioxide produced, which means that more reaction is occurring. Okay, now let me make this straight. Okay, so look here. In the first, okay, now first let me go for some illustrations. Okay, so in the first beaker, they have used HCl, okay, but they have used a lump or some solid particle of calcium carbonate. So what happened is that the amount of carbon dioxide lost from here, I think you can see it, the amount, these pink dots are the carbon dioxide. So a very small amount of carbon dioxide from here are lost per unit time. Okay, these are the carbon dioxide which is lost, for example. Okay, but when they have used the same HCl sample, but this time instead of the lump they have used highly divided same mass of calcium carbonate they have used, but they had now turned the calcium carbonate lump into powders by hitting it with a hammer, maybe, I'm not sure. Okay, so they have now spread out the amount of calcium carbonate, that means the reaction that means the reactants, the calcium carbonate has increased its surface area. So what happens is that the amount of carbon dioxide lost from over here, is more in a certain unit of time. More amount of carbon dioxide is lost. All right, okay, more amount of carbon dioxide is lost from here because the reactant particles are spread out, and so they would carry out more and more reaction between them, between this liquid body and the solid. Okay, liquid body and the solid. All right, so that's why, but the amount of carbon dioxide finally that would be produced would remain the same. Why? This is because we have used the same amount of reactants. The amount of product would depend on the amount of reactant. Please note it down. The amount of product would depend on the amount of reactant, and how quickly the products are formed depends on the rate of reaction. How quickly the products are formed depends on the rate of reaction, and the amount of products produced depends on the amount of reactants. So in both these cases the amount of reactants remain the same, so amount of carbon dioxide that would be produced is the same, but here in the second case the carbon dioxide will be produced at a higher rate. Okay, look over here. So this is, here they are using the lump of limestone, that means oh, I've got it rubbed off. Here they have used the lump of limestone, that means this one isn't this one, okay, the lump. And here in the second case they have used the powdered limestone, which is like this. Okay, the powdered limestone. So more surface area, more collision, more contact, and so more reaction, or the higher rate of reaction. Okay, but look, in the first case, what is the final amount of carbon dioxide produced? It is 5.6 gram. 5.5, okay, in the first case. And in the second case, oh, sorry, I'm wrong. So in the first case, the amount of carbon dioxide produced was 2 gram. In the second case, the amount of carbon dioxide produced was 2 gram. But let's look at the time required. Okay, here in the first case, the time required. I'm sorry that it was a call from one of my student. So here in the first case, in both cases, the amount of carbon dioxide which is produced is 2 gram, okay, but in the first case the time required to produce the 2.2 gram of carbon dioxide is about 6 minutes, okay. Now what about the second case? In the second case, the time required to produce the amount of carbon dioxide was 4 minutes, okay, and in the second case it is about not 6, it is about 5.5 minutes. So in which case was the reaction completed earlier? Obviously it's the second case, isn't it? Second case. So in the second case the rate of reaction must be higher, okay, but the amount of product remains the same because we have used the same amount of reactants, but here we have used the powdered reactant, the powdered limestone or calcium carbonate, okay. Now let's go into the second factor, which is the okay, which is the concentration. Simply, if you increase the concentration, then increasing concentration would increase the rate of reaction. Okay, I will show you this experiment in the class. It's not possible to show the experiment right now in the video. I will show it in the class. Okay, let's go to the discussion of concentration. Okay, now imagine that the reactant particles are red. The reactant particles are red and blue. Okay, so 1, 2, 3, 4, 5. Okay, first let me draw 2 boxes of same. Okay, so this is one box. Okay, so this is another box, and both of them have the same size almost. My drawing is not that much accurate. So red, 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 and green, 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 green. Okay, so this is one case. So here the red and the green particles would react. Okay, now in the second case we have red, 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 red. Okay, sorry. Red, red, sorry. Red, 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 red. Sorry. Okay, so now tell me, where are the particles more, the amount is higher? Okay, obviously in the second case, the amount of particles are higher in the same space, in the same volume. That means they have the higher concentration here. So here the particles have the higher concentration, and here the particles have the lower concentration. Okay, now tell me where the particles are closer and there is a more possibility, or there will be more number of collisions in a certain time. Obviously in the second case, because if the concentration is increased, then there are more number of particles and the particles are closer in the same space, so there would be more number of collisions. Okay, so that's why if the concentration is increased, the number of the rate of reaction would increase. Okay, now please write a note. If concentration is if concentration of a part of a reactant is increased, then there are more number of particles in a given volume, and so the particles are closer. So there is a higher chance and frequency of collision between the particles. There is a higher chance and frequency of collision between the particles, and so the rate of reaction would be higher. Okay? So that's the case of concentration. Now let's go to temperature. Okay? So before going into temperature, we must note a very important fact, which is that the temperature, let's see what the temperature do. Now temperature temperature actually increases the kinetic energy of moving particles. Okay? So temperature actually increases the kinetic energy of moving particles. Okay? What does this mean? This actually means, for example, this is a blue colored particle which was moving, okay, slowly. It was moving quite slowly, but when you are applying heat on this blue colored particle, that means you are increasing the temperature, then what's going on is that its movement speed would increase. Okay, that means they would move with higher velocities, with a higher speed. Now tell me, what about the collision between the two particles when they are moving at a lower speed or at a higher speed? Okay, for okay, now if okay, so let me draw two particles. For example, one particle is okay, so here are two particles. Now let me draw it far apart. Okay, so here are two particles. Now imagine if the particles are moving slowly. If the particles are moving slowly, then the collision between them would not be that much violent or may not cause a reaction because they are moving quite slowly. But if the particles move very fast, okay, if the particles move very fast, then there is a greater amount, or the collision between them will be extremely strong and they would react. Okay, isn't it? So when the temperature is increased, the particles or more particles now have higher amount of kinetic energy. So both the amount of collision and what you call the intensity of the collision increases. Intensity means how strongly they collide. Okay, so please write the note from here. When the temperature increases, the particles when the temperature increases, more particles now have higher kinetic energy, and so both the intensity and the frequency of collision between the particles increase. That means they collide more strongly with each other, and also they collide more often with each other because they are moving faster. Okay, so the rate of reaction would increase. Okay, so that's the matter of temperature. Now we have studied surface area, we have studied concentration, we have studied temperature, and now we are going to catalyst. Okay, now what does catalyst do? Okay, catalyst actually puts a discount on the amount of energy required to start a reaction. Okay, now what is the effect of discount over here? Let me tell you. Suppose you want to buy an ice cream which actually costs 50 taka or 50 bucks. Okay, you have 30 bucks, so you need what? You need more 20 bucks to buy the ice cream, isn't it? But what would a catalyst do? A catalyst would what have said? It would put a discount on the amount of energy. So that means if I put discount on the cost of ice cream, suppose the cost of ice cream is 40 taka, isn't it? Right now after 10 taka discount, and you have how many? You have 30 taka. So how much do you to have more? You need more 10 to make it 40. Okay, so only 10 is now required, but initially it was 20. Okay, so the amount of energy that you must put in, or you must provide more to start the reaction, is the activation energy. So catalyst does what? Catalyst does reduces the activation energy of a reaction. Okay, so that the particles which have lower amount of energy can now react. Okay, let me tell you one thing. For example, okay, let me go to my the lecture of chemical reactions. Okay, but I think instead of going to the YouTube videos, we can redraw a diagram over here. Okay, let's see. Let me get this straight. Okay, this is a box. This is a box. Okay, now I will be drawing some particles inside the box. Okay, so for example, now let me tell you that the energy of the particles is sequentially increasing in this direction. Okay, for example, this particle has got energy 1, this has got energy 2, this has got energy 3, energy 4, I mean the kinetic energy 5, then energy 6, energy 7, then energy 8. Okay, for instance, let's think that our activation energy is over here. Okay, so that means the particles, at least they must have 6 kilojoule or 6 joule of energy for the to carry out the reaction. Okay, that means this region, in this region the particles that are present are reactive. Okay, and the particles that are present in this region are the unreactive. Okay, So here the number of unreactive particles. So here just count how many unreactive particles are here. We have 1, 2, 3, okay, 2, 4, 6, 8, 10. So we have 10 unreactive particles. And how many reactive particles are here? 2, 4, 6. So we have 6 reactive particles. Okay. Okay, so we have 6 reactive particles. Okay, now what happens? So 6. Okay, now two, three. Okay, so now what does a catalyst do? A catalyst, what we have just learned, a catalyst puts a discount. That means it reduces the amount of energy that it reduces the amount of energy requirement, isn't it? Like you demanded 20 taka from the home before, when the cost of ice cream was 50, but now you demand only 10 taka from the home because the cost of ice cream has been reduced to 40. Okay, so now the energy that it remains the same. This is 1, this is 2, this particle has got energy 3, this has got energy 4 joule, 5 joule, 6, 7, 8 joule. Okay, just like over here that what we have put. Okay, now a catalyst, suppose, has now put the energy requirement line over here, sorry, over here. Okay, over here. Now, so the particles in this, so this is what we are calling it as the activation energy line. So the activation energy is now 1, 2, 3, 4. Okay, 4. So in this case the activation energy is 4. Okay. Okay, so the I rubbed it, sorry. Okay, so the particles in this region would be reactive. Okay, and the particles in this region would be unreactive still, because the minimum amount of energy that the particles must gain to start a reaction in this case is 4. Okay, so now count how many reactive particles are here. We have 1, 2, 3, 4, 5. That means 5 2s are 10. Now here, sorry, now here we have 10 reactive particles. So number of particles which are reactive, it will be equal to 10, and number of particles which are unreactive would be equal to 6, isn't it? 2, 4, 6. All right. Okay, so look, the number of reactive particles has increased, isn't it? Because catalyst has reduced the energy requirement, isn't it, by reducing the activation energy. So now the number of the number of particles remains same, but there were two classes of particles. One class was the unreactive particles, and one class were the reactive particles. So the catalyst has reduced the amount of energy requirement. So now the number of reactive particles has increased and the number of unreactive particles has decreased. Okay, so since the number of reactive particles have increased and now more particles have energy greater than the activation energy, isn't it? This is the activation energy. So more particles now have energy greater than the activation energy. So the rate of reaction would increase due to the use of catalyst. Okay. Now please write a note about catalyst. That catalyst reduces the activation energy required for a reaction so that there are now more reactive particles and less number of unreactive particles, and therefore, the rate of reaction would increase. Listen, the catalyst does not change the energy of particles, isn't it? This is very important. Look, here the particles has got energy 1, 2, 3, 4, 5, 6, 7, 8. As well as here the particles also has got the same energy 1, 2, 3, 4, 5, 6, 7, 8, but now just the energy that is required to start a reaction has decreased. Okay, like the quality of ice cream, as initially I was giving the example of ice cream, that's putting a discount. Initially the cost of ice cream was 50, but now the cost of same ice cream is 40, isn't it? So, what is now is going to happen, or better I put the example like this. Okay. So, ice cream has got the cost of 50, and now you what you have the amount 30. Okay. But somehow if you meet a man in the road who gives you 10 taka, ice cream at the shop cost 30 and you 50, you have 30, a man at the road gives you 10. Okay, so what you now have? You have 40. So how much do you need? You need only 10. But here in this case, how much do you need? You need 20. So the man has acted like a catalyst, because the man has helped you in reducing the amount of energy requirement you have. Okay, but it didn't change the value of the ice cream. Okay. Okay, let me give one more example of a catalyst. For example, suppose this is your home, okay, and this is your school, and you can go from home to school either by walking, okay, by walking, but that would take a lot of time. For example, it takes 1 hour, but you have called an Uber or a taxi that takes you to the school within 10 minutes. Okay, within 10 minutes. So look, the starting point and the ending point is the same. That means the reactant and the product is the same, or everything remains the same, just the time has been reduced. That means you have gone faster, isn't it? So the car or the taxi in this case is the catalyst, because it had reduced the time and has increased the rate of reaction. Okay, it has reduced the amount of time that you need or to invest. Okay, so now imagine that this car over here, after the car puts you to the school, will the car be destroyed, or that the cars or the quality of the car would be changed? No, not at all. The car will go into the road again and take some more passengers and work like this again and again. Okay, so the quality of the car or the appearance of the car remains unchanged after the car has put you into the school. Okay, so the catalyst in this case is the same. So write the properties of catalyst. Number 1, a catalyst reduces the activation energy requirement for a reaction. Okay, this is number 1. Now write number 2, that the catalyst reduces the amount of time and therefore increases the rate of reaction without changing the energy of the particles, because few moments ago I have said that kinetic energy of the particles or movement energy of the particles depends only on the temperature. Okay? So, number 3, a catalyst remains unchanged at the end of reaction. A catalyst remains unchanged at the end of reaction. Some books says that a catalyst does not take part in the reaction, but this is actually wrong. Actually, that most of the catalyst takes part in the reaction, okay, but it remains unchanged at the end of reaction. Okay. So, since it remains unchanged at the end of reaction, so a catalyst can be used over again and again. This is number 4. A catalyst can be used over again and again. Okay. So, these are the properties of catalyst. Okay. Now, let us go to the next factor, which is the pressure. Okay, I am just saying, please write it down. Okay, according to Boyle's law in physics, the Boyle's law of gas pressure, you know that if pressure is increased, then the volume of the gas would decrease, as we know that pressure is inversely proportional to the volume. So, if the pressure is increased, the volume of gas would decrease. Okay. Now, just imagine that you have okay, no, not this. You have a container, and here this is a piston, okay, and you have the same container over here, but the piston is compressed and the volume is decreased. Okay, the volume is decreased. Okay. Now, I will be drawing 1, 2, 3, 4, okay, 5, 6, 1, 2, 3, 4, 5, 6, 7. Okay. Now, tell me that where the particles are closer, is it in the first state or in the second state? Here we are applying a pressure. So, in the second state the particles are more closer, isn't it? So, the particles are more closer. So, there is a greater chance of collision, and there will be greater number of collision between the particles per unit time. Okay. So, here since the particle will collide more often, so the rate of reaction would increase, but this is applicable only in case of gases. Okay. Because the pressure is inversely proportional to the volume. This is the law for gas. Okay. So, now write the note, please. If the pressure is increased on a gas reactants, then the particles would collide, the particles would be more closer due to reduction in volume, and therefore, there is a greater chance and frequency of collision between the particles. So, the rate of reaction would increase. Okay. So, that is the case of pressure. Okay. So, enzymes, enzymes are simply the biological catalysts. Okay. So, the enzymes, they are also some type of catalyst, but the difference is that these catalysts are found within only the living things. Okay. Only living things. Living things. Okay. And these catalysts are not as robust as the industrial catalysts, but these catalysts can be they are very much sensitive. And please write the properties of these catalysts, I mean the enzymes. Please give the headline, the properties of enzymes. Number 1, enzymes are biological catalysts which are all proteins. That means all enzymes are proteins. Okay. Now, number 2. One enzyme can be used as catalyst for only one specific reaction. Okay, one enzyme can be used as catalyst for only one specific reaction. Okay, like for example, I am telling two reactions. Respiration, for example. Okay, respiration, it's like C6H12O6 is broken down to release energy. Okay, so this process has got a specific enzyme or something like that. Or and again, for example, amino, or we can say that protein, we can say that protein is broken down to amino acid, or starch is broken down to produce glucose. So these are two different reactions. So these two different reactions will employ the use of two different enzymes. Okay. So enzymes are specific for a specific reaction or a particular reaction. Now, number 3, enzymes work best at temperature around 40 degrees Celsius. Okay, enzymes work best at temperature around what? 40 degree Celsius, and they are destroyed, or in biological sense we call it denatured. They are destroyed or denatured at higher temperatures, maybe 45 or 40, whatever it is. Okay, then number 4, enzymes are extremely sensitive to changes in the amount of hydrogen ions. Okay, changes in the amount of hydrogen ions. Hydrogen ions, you know, it's H plus, and amount of hydrogen ions can be expressed in one word as pH. So we can also say enzymes are extremely sensitive to changes in pH. Okay. Okay, so guys, that's all for the properties of enzymes. And what you will do is that you must go through my lecture, this lecture again and again, then read this summary over here. If you need a copy of this book, please knock me in WhatsApp, although I have given it in my WhatsApp group. And so now, and what you would do further is that you will do these questions, and I will be uploading a solving video of all worksheets or the homeworks that I am giving from the from this coming Monday. Okay, all right. And if you have any still further problem, we will be discussing it in the class. Okay, guys. So that's all for today. We will meet inshallah on Monday. Okay, till then, goodbye.